we now have the tools, I think, to understand the idea of a linear subspace of Rn. Let me write that down. And I'll just write it, I'll just always call it a subspace of Rn. Everything we're doing is linear. Subspace of Rn. I'm going to make a definition here. I'm going to say that a set of vectors v, so v is some subset of vectors, some subset of Rn. So we already said Rn, when we think about it, it's really just really an infinitely large set of vectors where each of those vectors have n components. So, I'm going to not formally define it, but this is just a set of vectors. I mean, sometimes we visualize it as multi-dimensional space and all of that. But if we wanted to be just as abstract about it as possible, it's just all the set. It's the set of all of the, we could call it x1, x2, all the way to xn, where each of the xi's are a member of the real numbers for all of the i's. Right? That was our definition of Rn. It's just a huge set of vectors, an infinitely large set of vectors. V, I'm going to call that a subset of Rn, which means it's just some, it could be all of these vectors, and I'll talk about it in a second, or it could be some subset of these vectors. Maybe it's all of them, but one particular vector. And in order for this V to be a subset, to be a subspace, so I'm already saying it's a subset of Rn. So if I were to, maybe this will help you. If I draw all of Rn here as this big blob, so these are all of the vectors that are in Rn. V is some subset of it. It could be all of Rn. I'll show that in a second. But let's just say this is V. V is a subset of vectors. It is a subset of vectors. Now, in order for V to be a subspace, and this is a definition, if V is a subspace, or linear subspace of Rn, this is my definition. This means three things. This means that V contains the 0 vector. V contains, that's the 0 vector. Or this is equal to 0 all the way, and you have n zeros. So V contains the 0 vector, and this is a big V right there. If we have some vector x in V, so let me write this. So it's x. If my vector x is in V, if x is one of these vectors that's included in my V, then when I multiply x times any member of the reals, so if x is in V, then if V is a subspace of Rn, then x times any scalar is also in V. This has to be the case. And for those of you who are familiar with the term, this term is called closure. If I have any element of a set, and then this is closure under multiplication. Let me write that down into a new color. This is closure under scalar multiplication. And that's just a fancy way of saying, look, if I take some member of my set, and I multiply it by some scalar, I'm still going to be in my set. If I multiply it by some scalar and I end up outside of my set, if I ended up with some other vector that's not included in my subset, then this wouldn't be a subspace. In order for it to be a subspace, if I multiply any vector in my subset by a real scalar, I'm defining the subspace over real numbers. If I multiply it by any real number, I should also get another member of this subset. So this is one of the requirements. And then the other requirement is if I take two vectors in my, let's say I have vector A, it's in here, and I have vector B in here. So if this is my other requirement for V being a subspace. If vector A is in my set V, and vector B is in my set V, then if V is a subspace of Rn, that tells me that A and B must be in V as well. So this is closure under addition. Let me write that down. Closure, closure under addition. Once again, just a very fancy way of saying, look, if you give me two elements that's in my subset, and if I add them to each other, and these could be any two arbitrary elements in my subset, and I add them to each other, I'm going to get another element in my subset. That's what closure under addition means. That when you add two vectors in your set, you still end up with another vector in your set. You don't somehow end up with a vector that's outside of your set. So if I have a subset of Rn, so some subset of vectors of Rn that contains the 0 vector, and it's closed under multiplication and addition, then I have a subspace. So a subspace implies all of these things, and all of these things imply a subspace. This is the definition of a subspace. Now, this might seem all abstract to you right now, so let's do a couple of examples. And I don't know if these examples will make it any more concrete, but I think if we do it enough, you'll kind of get the intuitive sense of what a space implies. I mean, well, let me just do some examples, because I want to stay relatively mathematically formal. So let's just say I have the almost trivially basic set. Let's say my set of vectors, I only have one vector in it, and I have the 0 vector. So I'll just do a really bold 0 there. Or I could write it like this. The only vector in my set is the 0 vector. And let's say we're talking about R3. So let's say my 0 vector in R3 looks like that. So what I want to know is my set V, is V a subspace of R3? Well, in order for it to be a subspace, three conditions. It has to contain the 0 vector. Well, the only thing it does contain is the 0 vector. So it definitely contains the 0 vector. So 0 vector, check. Now, is it closed under multiplication? So that means if I take any member of this set, there's only one of them, and I multiply it by any scalar, I should get another member of the set, or I should get maybe itself. So let's see, there's only one member of the set. So the one member of the set is the 0 vector. If I multiply it times any scalar, what am I going to get? I'm going to get c times 0, which is 0, c times 0, which is 0, and c times 0. So I'm going to get its only member. But it is closed. So it is closed under multiplication. Under multiplication. You can multiply this one vector times any scalar, and you're just going to get this vector again. So you're going to end up being in your 0 vector set. That's a check. Now, is it closed under addition? Well, clearly, if I add any member of this set to itself, or I mean, there's only one member, or to another member of the set, there's only one option here. If I just add that to that, what do I get? I just get that. I just get it again. So it definitely is closed under addition. Check. So it does turn out that this trivially basic subset of R3 that just contains the 0 vector, it is a subspace. It is a subspace. Maybe a trivially simple subspace, but it satisfies our constraints of a subspace. You can't do anything with the vectors in it that'll somehow get you out of that subspace, or at least if you're dealing with scalar multiplication or addition. Now let me do one that maybe the idea will be a little clearer if I show you an example of something that is not a subspace. So let me get my coordinate axes over here. So let's say I were to find some subspace, some subset. I don't know whether it's a subspace. Let me call my set S, and it equals all the vectors. It equals all the vectors. Let me say x1, x2 that are a member of R2, such that I'm going to make a little constraint here, such that x1 is greater than or equal to 0. So it contains all of the vectors in R2 that are at least 0 or greater for the first term. So if we were to graph that here, what do you get? We can get anything. We can move up or down in any direction, right? So we can go up and down in any direction, but we're constraining ourselves. These are all going to be 0 or greater. So all of these first coordinates are going to be 0 or greater. So we're going to, and this one, we can go up and down arbitrarily. So we're essentially, this subset of R2, R2 is my entire Cartesian plane. But this subset of R2, it'll include the vertical axis, often referred to as the y-axis. It'll include the vertical axis, and essentially the first and fourth quadrants. If you remember your quadrant labeling, so that's the first quadrant, and that's the fourth quadrant. So my question to you is S a subspace of R2? So the first question, does it contain the 0 vector? So in the case of R2, does it contain 0, 0? Well, sure. It includes 0, 0's right there. We said x is greater than or equal to 0. So this could be 0. And obviously, there's no constraint on this. So definitely, the 0, 0 vector is definitely contained in our set S. So that is a check. Now, let's try another one. If I add any two vectors in this set, is that going to be is that also going to show up in our set? Well, let me just do a couple of examples. Maybe this isn't a proof. Let's see. If I add that vector to that vector, what am I going to get? If I put this up here, I'm going to get that vector. If I add that vector to that vector, what am I going to get? I could put this one head's tail. I would get a vector that looks like that. And if I did it formally, if I add, let's say that I have two vectors that are a member of our set. So let's say the first one is AB, and I add it to CD. What do I get? I get A plus C over, this was a D, over B plus D. So this thing is going to be greater than 0. This thing is also going to be greater than 0. That was my requirement for being in the set. So if both of these are greater than 0 and we add them to each other, this thing is also going to be greater than 0. And we don't care what these can be anything. I didn't put any constraints on the second component of my vector. So it does seem like it is closed under addition. Closed under addition. Now what about scalar multiplication? Let's take a particular case here. Let's take my AB again. I have my vector AB. Now, I can pick any real scalar. Remember, it doesn't, so any real scalar. Or what if I just multiply it by -1? So -1. So if I multiply it by -1, I get minus A minus B. So if I were to draw it visually, if this is, let's say AB was the vector 2, 4, so it's like this. When I multiply it by -1, what do I get? I get minus A minus B. I get this vector, which you can visually clearly see falls out of, if we view these as kind of position vectors, it falls out of our subspace. Or if you just view it not even visually, if you just do it mathematically, clearly if this is positive, then this is going to, and let's say that we assume this is positive and definitely not 0, so it's definitely a positive number, so this is definitely going to be a negative number. So when we multiplied it by -1, for really any element of this that doesn't have a 0 there, you're going to end up with something that falls out of it, right? This is not a member of this set, because to be a member of the set, your first component had to be greater than 0. This first component is less than 0. So this subset that I drew out here, the subset of R2, is not a subspace because it's not closed under multiplication or scalar multiplication. Not closed under scalar multiplication. Not closed. So this is not a subspace, of R2. Now, I'll ask you one interesting question. What if I ask you just the span of some set of vectors? Is that a valid? Let's say I have the span of some. Let's say I want to know the span of I don't know. Let's say I have vector v1, v2, and v3. And I'll be, I'm not even going to tell you how many elements each of these vectors have. Is this a valid subspace? Valid subspace of Rn, where n is kind of the number of elements that each of these have, of Rn. Well, let's pick Ed, let's pick one of the elements of, let me define, let me just call U to be the set, the set of all linear combinations of this is the span. So let me just define U to be the span. So I want to know, is U a valid subspace? So let's think about it this way. Let me just pick out a random element of U. Let me pick out a random element of U. Actually, does this contain the 0 vector? Well, sure. If we just multiply all of these times 0, so if we just say 0 times v1 plus 0 times v2, these are all vectors. I didn't write them bold, plus 0 times v3, we get the 0 vector, right? Everything just is zeroed out. So it definitely contains the zeroed vector. This is a linear combination of those 3 vectors. So it's included in the span. Now, what if let me just pick some arbitrary member of this span. So in order to be a member of this set, it just means that you can be represented. Let me just call the vector x. It means that you can be represented as a linear combination of these vectors. So some combination c1 times v1 plus c2 times v2 plus c3 times v3. Right? I'm just representing this vector x. It's a member of this, so it can be represented as a linear combination of those 3 vectors. Now, is this set closed under multiplication? Well, let's just multiply this times some arbitrary constant. What is c times x? Let me scroll down a little bit. What does c times x equal? Let me do a different constant, actually. Let me multiply it times some arbitrary constant a. What is a times x? Well, it's a times c1 times v1. I'm just multiplying both sides of this equation times a. A times c2 times v2 plus a times c3 v3. Right? Well, you could just, if this was an arbitrary constant, you could just write this as another arbitrary constant. This is another arbitrary constant. And this is another arbitrary constant. And I want to be clear. All I did is I just multiplied both sides of this equation times a scalar. But clearly, this expression right here, I could rewrite this as, c4 times v1 plus c5 times v2, where this is c5, this is c4, plus c6 times v3. This is clearly another linear combination of these 3 vectors. So the span is the set of all of the linear combinations of these 3 vectors. So clearly, this is one of the linear combinations, so it's also included in the span. So this is also in U. It's also in the span of those 3 vectors. So it is closed under multiplication. Now we just have to show that it's closed under addition, and then we know that the span of, I did 3 here, but you can extend it to an arbitrary n number of vectors, that the span of any set of vectors is a valid subspace. So let me prove that. So we already defined one x here. Let me define another vector that's in U, or that's in the span of these vectors. And it equals, I don't know, let's say it equals d1 times v1 plus d2 times v2 plus d3 times v3. Now what is x plus y? If I add these 2 vectors, what are they equal to? Well, I could just add x plus y means all of this stuff plus all of this stuff. And so what does that equal? It means if you just add these together, you get c1 plus d1 times v1 plus c2 plus d2 times v2 plus c3 plus d3 times v3. Right? You had a v3 here. You had a v3 there. You just add up their coefficients. Clearly, this is just another linear combination. These are just constants again. That's an arbitrary constant. That's an arbitrary constant. That's an arbitrary constant. So this thing is just a linear combination of v1, v2, and v3. So it must be, by definition, in the span of v1, v2, and v3. So we are definitely closed under addition. Now you might say, hey, Sal, you're saying that the span of any vector is a valid subspace, but let me show you an example that, clearly, if I just took the span of one vector, let me just define U to be equal to the span of just the vector. Let me just do a really simple one. Let's say it's just the vector 1, 1. Clearly, this can't be a valid subspace. Let's think about this visually. So what does vector 1, 1 look like? Vector 1, 1 looks like this, right? And the span of vector 1, 1 is all of, and this is in its standard position, the span of vector 1, 1 is all of the linear combinations of this vector. Well, there's nothing else to add it to, so it's really just going to be all of the scaled up and scaled down versions of this. So if you scale it up, you get things that look more like that. If you scale it down, you get things that look more like that if you go into the negative domain. So just by multiplying this vector times different values, and if you were to put them all into a standard position, you would essentially get a line that looks like that. And you say, gee, that doesn't look like a whole subspace. But a couple of things. Clearly, it contains the vector 0. It contains the 0 vector. We can just multiply 0 times 1. We can just scale it by 0. Right? The span is just all of the different scales of this. And if there were other vectors, you would add it to those as well. But this is clearly going to be the 0 vector. So it contains the 0 vector. Is it closed under multiplication? Well, the span is the set of all of the vectors, where if you take all of the real numbers for C and you multiply it times 1, 1, that is the span. So clearly, you multiply this times anything, it's going to equal another thing that's definitely in your span. Now the last thing, is it closed under addition? Is it closed under addition? So any two vectors in the span could, let's say that I have one vector A that's in my span. I can represent it as C1, some scalar times my vector there. And then I have another vector, B, and I could represent it as C2 times my one vector in my set right there. And so what is this going to be equal to? This is going to be equal to, this is essentially going to be equal to well, let me get a little more space. This is going to be equal to C1 plus C2 times my vector. Right? This is almost trivially obvious. But clearly, this is in the span. It's just a scaled up version of this. This is in the span. It's in a scaled up version of this. And this is also going to be in the span of this vector, because this is just another scalar. We could call that C3. And if you just do it visually, if I take this vector right there, let's say I take that vector, and I were to add it to this vector, if you put them head to tails, you would end up with this vector right there in green. I don't know if you can see it. Maybe I'll do it in red right there. You will end up with that vector. And you could do that. Any vector plus any other vector on this line is going to equal another vector on this line. Any vector on this line multiplied by some scalar is just going to be another vector on this line. So you're closed under multiplication, you're closed under addition, and you include the 0 vector. So even this trivially simple span is a valid subspace. And that just backs up the idea that we showed here, that in general, I could have just made this a set of n vectors. Right? I picked 3 vectors right here, but it could have been n vectors, and I could have used the same argument, that the span of n vectors is a valid subspace of Rn. And I showed it right there.